So what we want to do is find this z-score. Where is our z-score landing in terms of our distribution? However, since we're using our normal curve here, we need to make sure that our samples would behave this way, that we would have this normally distributed curve. In order to check that, we need to make sure we pass those conditions that we had for a sampling distribution of proportions. So what we'll need to do is check those conditions that we talked about, and actually we described it as 3 conditions. That 10% condition can kind of go with independence. So first thing we need to check is that all of our results are independent of each other. So there shouldn't be any influence, or you can check that we sampled less than 10% of our population, and that guarantees independence there. We should have randomization, making sure that we have a random sample, and again, sometimes we have to assume this if it doesn't clearly state that. And then what we also have is the sample size condition, or it's also described as the success failure. And remember, with our proportions, that's where we take our sample size times our population proportion, and our sample size times 1 minus that value, and make sure both of those are at least 10. So what's going to happen with these hypothesis tests are that there's going to be kind of 2 proportions we're working with simultaneously. There's always going to be sample data, so we're going to have the sample proportion, and then we have this assumed proportion for our population. Now what we want to think about with these curves that we're building, and this is what we're checking the conditions for, the curve that we're building is all about the null hypothesis being true. We're trying to base this on that assumption is true, and then where does the sample land? So when we're checking our conditions and building this curve, it's all about the null hypothesis, which means the proportion that we want to use is 0.5. We want to use this throughout the building of this bell-shaped curve. Really, this sample is only going to come in at one spot and check to see how extreme it is in getting that z-score. So we want to build it around this hypothesis. So when we check our conditions, be sure that these proportions are coming from the hypothesis. And that's where we use the subscript of 0. So it's like our null proportion, our null hypothesis proportion. So be sure to check the null hypothesis when checking your sample size. We don't want to check it against our sample proportion because that's not what we're building the curve around. We want to use those values. So before we can calculate that z-score, we need to make sure we pass these conditions. So for our example, checking our conditions, first, making sure our results are independent. So the game results should be independent of each other, or the fact that we only looked at 245 NFL games, that's less than 10% of all NFL games. So we're going to be okay with independence. Randomization actually kind of looks like this isn't a very random sample with it all coming from the same season, but we're just going to assume that that's random enough so we can move forward. And then we need to check our sample size, which we're taking that 245 as our sample size, and then we need to multiply it with P and Q. And again, P, when we have these kind of 2 values of proportions, we want to use the one in the hypothesis. So grabbing that P equals 0.5, and checking that, and then 1 minus 0.5, which is actually just the same. And this will check our sample size, which those values should be 122.5 for both of those. And since both of those are more than or equal to 10, we're good there. So we check our conditions, and that lets us move forward. So what we want to do next is find this z-score. And if we recall, the formula for our z-score that we looked at is taking that x value minus the mean over standard deviation. But let's kind of put this into more vague terms. This x here is some sample data. So that's coming from a specific sample that we want to check out, kind of see how extreme is this value compared to the mean and standard deviation, minus, and how about instead of mean we say expected value? Those we can use interchangeably, divided by the spread of our data. So this is another way we can think about z-score. Is we have some sample value that we want to see the distance from where we expect to be, and then we want to divide that by how it spreads, by standard deviation. So what we're going to do for our z-score, this is called our test statistic. Finding our test statistic, we want to take our sample data, which for us is our sample proportion. And we want to see how far away is it from where we expect to be landing, which for us, the curve that we're creating, our expected value is always going to be this proportion from our hypothesis. This is where we assume that we're going to land. So we want to see how far away we are from that hypothesized proportion, and then divide that by the spread of the curve. Which again, this is linking to our sampling distribution of proportions, which if you remember the standard deviation for those curves, you take your square root of p times q over n. And where we have p and q here, again, the spread of this curve, we want to keep linking back to our hypothesis. We want to be assuming this is true, so the spread of the curve would depend on our hypothesized proportion. So that's where these values should be coming from, is from the hypothesis. So throughout this whole process, use that sample statistic in one spot, and it's right here. Everything else is using that value for p from the null hypothesis. So for us, what we'd be calculating is taking that 0.6245 minus our hypothesized proportion of 0.5 divided by this big square root symbol of taking 0.5 times 1 minus 0.5, which is also just 0.5, divided by our sample size of 245. So if we plug this into a calculator, whatever system we're using, just be careful with those parentheses. Make sure you're grouping that numerator together. And then also make sure everything under this square root symbol stays together. So what this will look like for us is plugging in 0.6245 minus 0.5, and then having parentheses around those, and then starting your square root symbol and just making sure everything stays underneath there. And we get out our z-score of 3.8975. So what this tells us is where we're landing in our standard normal curve. If we have our mean of 0, standard deviation of 1, we're getting out this about 3.9, which means we're landing pretty far out there. If you remember when we talked about these standard deviations away, we talked about anything more than 2 standard deviations away as kind of extreme. That's going to link through here. We have this big z-score, which is going to be telling us that this is an extreme sample result. But to really prove that, we want to find that probability, that in this case the area to the right of that curve. So finding the probability using our standard normal curve, we're going to use technology to find this probability of being more than or equal to 3.8975. And when we plug this into technology, it's going to give us about 0. And this is the probability that's going to be telling us whether or not we have evidence. So let's talk about this. What is this actually saying, getting this probability of 0 out? So through this whole process, we're assuming there's no home field advantage. We're trying to prove that there is a home field advantage. So through this process, assuming there is no home field advantage, what we just showed is that to have these results, to have this proportion of 0.6245, there's almost a 0% chance of seeing these sample results if this is true. which basically means this 2013 season, if there's no home field advantage, is pretty much an impossible season. Pretty much. Not completely impossible, but with so close to 0%, highly unlikely for this to occur if this is true. So what that links to is this probably isn't true. We're getting evidence that this can't be true if we had these results. They're just too extreme, and it's more likely that our proportion's larger. This whole distribution that we built here is actually further to the right somewhere where this is a more likely occurrence. Because where I drew this picture, 0.6245 is actually way out here, way far away. And that's where we're seeing these extreme results, which means if we have these extreme results, it's just so likely to occur if that's accurate, which means we're getting evidence that that's not accurate. So what this says, if there is no home field advantage, there is close to 0% chance of seeing these 2013 results, or more extreme. Again, that probability we're finding shades to the right, so it's seeing a proportion that large or even larger. So if there's this pretty much 0% chance of seeing that sample statistic, that means our sample statistic, p hat, is giving evidence that our null hypothesis is false. And we're getting evidence that the alternative is true. So it links with this probability being so small that we get to reject that null hypothesis, and we have evidence for that alternative. And that comes through matching this scenario of this small area being created, and even though there's always a possibility, like even with 0%, way out there in the decimal places, there is a possibility of this occurring under that distribution, but it is just so unlikely, way too unlikely to occur. And with that, we're saying we have evidence for this. But the other scenario can always come through, which is where we get a large probability. So we got a probability of 0. If we had like a probability of, say, 15%, saying there's a 15% chance of seeing those sample results or more extreme, that's where we end up not getting evidence to reject that null hypothesis. If we end up with a large probability, we can't reject this, therefore don't have enough evidence to claim the alternative. So that's where we end up with these two scenarios. This probability that we find, this is called p-value. P-value is going to be this probability of seeing a sample statistic occur given our null hypothesis is true. So this p-value is where we see whether or not we have evidence for our alternative hypothesis. So, the two scenarios. First scenario is that we get to reject that null hypothesis. This is where the p-value is small. This is where we're getting that small probability coming through, which is what we saw up here. This is the smallest possible probability we could get, and that means we get to reject the null hypothesis. And alternatively, we could describe it as statistically significant results and we have evidence for the alternative hypothesis, which is exactly what we want. We want to prove that alternative hypothesis, and that's going to come through when that p-value is small. The other scenario is where we failed to reject the null hypothesis, where we haven't been able to prove that it's false, and that happens when the p-value is not sufficiently small. And we'll talk about what makes it small versus not sufficiently small. But this is where we end up with insufficient evidence for the alternative hypothesis. This is where we just can't quite prove that alternative with the sample results that we have. The key is the smaller the p-value, the stronger the evidence for the alternative. So with that small p-value, we're getting more and more evidence for the alternative. And in our case, we have the strongest possible evidence for our alternative hypothesis right here. We really proved that there is a home field advantage. So let's put that all together. Determine if you should reject the null hypothesis or fail to reject. Well, we had a p-value close to 0, which is very small. It's basically the smallest we can see in terms of a probability being 0. So when we end up with this very small p-value, that's where we reject the null hypothesis. Meaning where our null hypothesis was that there is no home field advantage and the alternative is that there is, what we're essentially doing is our sample was so extreme that can't be true. Instead, we have evidence that this is actually true. And writing our summary, we always want to state the p-value, because that p-value is talking about the probability of seeing our sample given the null assumption, given this is true. So with that, that's where we link back to kind of stating the % chance that we're incorrect. So we always want to start by saying the p-value. So for us, with the p-value close to 0, and then we talk about what did we prove. And you could say like the proportion of home games won is more than 0.5, or you can put into the context of the situation, which is that this was the idea of no home field advantage, and this is the idea of there is a home field advantage. So you'd say there is evidence of a home field advantage. And that would be our conclusion to this hypothesis test. Now, our hypothesis test will run a little more smoothly than this one. I mean, this was an introduction, definitely. But our hypothesis tests are going to be broken down into 4 steps. Our first step is going to be stating that null and alternative hypothesis. So for us is putting together this statement right here, and we're going to practice for different scenarios putting those statements together. Then we're going to have a step where we need to check the conditions for using the normal model. So we always need to go through checking these 3 conditions to make sure we can move forward. And something we're going to throw into this step a little later on is setting up the test, getting kind of a visual of how we'd move forward and finding that p-value. And then we're going to have the step of calculating the test statistic and the p-value to evaluate. And that's what's going to come through with these 2 pieces. Calculating our test statistic will come through with this formula right here. So we'll be calculating a test statistic using this. And then once we have that z-score, we go and find the p-value, which is this finding this probability under the curve using that z-score. And then we'll get some probability that's our p-value. And once we have that, we can evaluate, do we reject the null or fail to reject the null? And once we can figure out which way we go with the p-value, we write a summary. It's going to end up being a single sentence like this where we state our p-value, and it's going to be whether or not we have evidence for the alternative hypothesis. So we'll go through practicing each of these steps, and we'll have a few examples, and I'll give you an outline of how to go through this. What we're going to do next, though, is look at how do confidence intervals connect to these hypothesis tests. So that'll be in our next video.